Thanks for that. So this work is part of the CakeML project. So I'm going to start out just by giving you a little bit of context about what the CakeML project is trying to do. So what we want to do is see how far we can push full-on sort of formal verification. So we want to have programs. We want to have full specifications of what those programs do. And then we want to be able to prove without any doubt, so all our proofs want to be formally machine-checked proofs, in our case, in the Hall 4 theorem prover. We want to prove that the actual machine code that's going to be running sort of is correct according to what we think the machine code should be doing. And we want that to be, with respect to a model of the operations of the x86 or ARM or RISC-V or whatever sort of processor, sort of off-the-shelf processor that you're going to be running. Right, so that's our ultimate goal of the whole project. Now, you could approach this by saying, well, we'll write some machine code, and then we'll have a separation logic about machine code, and we're going to verify that. But I think that would be a complete non-starter. So what we really want is a nice programming language that we can verify programs in, and then have a compiler generate the machine code for us, right? So because functional programming is wonderful and easier to reason about in some cases, especially if it's pure functional programming, that's why we choose an ML program, an ML-like programming language to do our reasoning about. And then sort of we're going to need a compiler that we can trust. So that means we need a fully verified compiler. So we need a theorem checked in the Hall 4 theorem prover that says when you run the compiler, sort of the source program, according to the semantics of the programming language, sort of has the same behavior as the actual machine code that the compiler generates, according to the actual semantics of our sort of testable model of the x86 or the ARM or the MIPS processor. Right? So that's the compiler is sort of the centerpiece, and then this paper is talking about one particular optimization that compiler does. And I think it's an interesting optimization because it's at the heart of what a compiler for a functional language needs to do to get any sort of efficiency at all. Now, I'll say that, like a lot of formal verification research of building a big system, the contributions are in two different kinds. Right? One of our contributions is to say, look, we've built this realistic compiler and we've formally verified it. Right? This is something you can do with formal verification. Right? So that's one contribution. And then the other sort of contribution is, here are a whole bunch of little technical things that we learned about doing the verification. And if you were to go and do a similar verification yourself, you should sort of know all of these little things that have been learned beforehand. And I'm sorry to disappoint anyone who really wants to learn a whole bunch of little cool verification tips. But in this talk, I'm going to mostly be focusing on the first aspect, which is sort of what is this thing we've built? Why is it interesting to verify? Right. So that's by way of introduction. I'm now going to say, what have we actually done? Well, here's a program. Right. You should be able to, it's in standard ML syntax, and it is the sort of naive, non-tail recursive quadratic reverse function for a list. And really, the only thing that we're talking about in this talk relative to this program is these function calls. When I call append, when I call reverse, I want those function calls to go fast. I don't want to do what the semantics suggests that I should do and have a closure come in, look at the pointer in the closure, do an indirect jump to that closure. I want the compiler to recognize, hey, when you call append here, when you call rev here, I know at compile time exactly what function you're going to be calling. It's not a very complicated analysis to figure that out. So I just want to emit code that pushes the stack and then does a jump, right, to a hard-coded compile time known address. So that's one optimization that I'm really going to have to do. The other optimization that I really want to do is in the case where I'm calling an unknown function, right, and I'm in the context of a curried ML or Haskell-like language. I don't, again, want to do the naive thing that looking at the semantics would suggest you do, which is feed the first argument into f, allocate a closure, feed the second argument into f, and then get on with the work. We want to be able to turn that into a true sort of C-style multi-argument function call, right? And I want to be able to do that, if I've got map 7 or something where I feed lots of arguments in, I want to be able to do a 7-argument function call. So that's where we're going. Those are the optimizations we want to do. But first, I'm going to spend quite a bit of time explaining sort of the context of the KKML language and the semantics and the compiler so that you can understand sort of where these optimizations are fitting in the world, right? But I also want to say a big thank you to our last speakers from yesterday for giving me this wonderful compiler bug, because you may have wanted to tell me, oh, come on, how hard could it be to just introduce multiple argument functions and get them right? But of course, they found this real bug in the OCaml compiler was exactly, it was introducing some multi-argument functions when it was in fact unsound to do so and not getting it right. So we have a proof that we don't have this bug. Right. So the KKML language, and I've given you a quick sort here, just if you prefer to learn by example, that's what it looks like. It's basically a subset of standard ML, although as time goes on, we sort of make design decisions that make us drift from that a bit. But we're strongly typed, we're call by value, we encourage an OCaml-style curried programming rather than the SML tupled style of programming. But because we want to target sort of real systems applications eventually, distributed whatever, and we want to be able to do I/O and all of that sort of thing, we are an impure language with state and exceptions and all of that sort of stuff. So really thinking a pretty healthy subset of standard ML, recursive functions, pattern matching, sort of, other than the complicated module system stuff like functors, which we just haven't got around to yet because the need hasn't arisen. We're a pretty full-on standard ML sized language. Right. What's our compiler look like? So this isn't really for you to read, although I do see some heads turning sideways. This is the joy of widescreen slides, right? Has to go this way. If you want to look at this diagram, it's available on our webpage here. And feel free to peruse that. This is sort of what our compiler is, all of the different phases that it goes through. I can summarize that just by saying a compiler is a function that takes a string and gives you back a number, right? How do we get there? Well, we start with a verified lexer, a verified parser, a verified type inferencer. We have a verified type soundness proof. Then we've got 12 intermediate languages, i.e. the thing on the top of the picture, verified optimizations to take you through all of those. And then we have sort of a generic assembler that does instruction selection and resolves all of the labels and the jumps and all of that low-level stuff, also verified, to give us machine code. So that's what the compiler looks like. We've seen the language, we've seen the compiler. I've been talking an awful lot about reasoning and verification. So what's coming next? The semantics, right? And the semantics are very similar to the semantics of standard ML, sort of extensionally speaking. But intentionally, the form of the semantics as we write them down is quite a bit different. And we do this because we found this style of semantics really helps our proofs work. So we do something called functional big step semantics, which was the topic of a previous paper from ESOP 16, so I don't want to go into too much detail. All I really want to do is evangelize this a bit. So our formal semantics, which we found to be very convenient for doing all of our proofs with respect to, look exactly like the interpreter. So this is the if case. I pulled the if case off just because it's one of the simplest cases in the language. And it looks, okay, it's a bit ugly. This would look better with do notation. But this is just a state, it's sort of state exception monad, what you would write as an interpreter. And so we use basically interpreters for our formal semantics. The only hitch is because we've got recursive functions, these interpreters may not terminate, and so for logical reasons, we have to put a clock on it. Right? But that's not really what I'm here to talk about. But I think you should all give it a go. Right. So also, I mean, we're not crazy. We're not the only ones doing this. Jeremy Sieg has been suggesting this for a while, and Amin and Ramph have been recently using this style of semantics in some of their recent work. So is it's just when it works, it's a really nice way of setting up your semantics. Okay, so that's big picture. Let's zoom in a bit more now. The particular language that we're going to do these function call optimizations in, the particular intermediate language, is called Closslang, short for closure language. And you should think of Closslang, it's basically an untyped lambda calculus, but we've got De Bruijn indices which are going to help us sort of in the general theorem-proofy way that De Bruijn indices do. We've got a table of global variables, we have state and exceptions still, and we have lots of primitive data and operations for the various sort of things that our programming language operates over. But we've already compiled away some complicated things like modules and data type constructors and patterns. So we've got it's sort of lambda calculus plus some stuff that we still have to have around. Right. And so now I've zoomed in here on that sideways picture before, and you can actually read this. So when we get into Closslang, what is the compiler going to actually do? Well, first of all, it's going to run through the code looking for multi-argument functions and multi-argument applications to sort of merge those all together, get rid of as much carrying as it possibly can. Then it's going to do a bit of data flow analysis to track where the values, where these function closures flow in the program. And then when it says, I know what function you're calling here, it's going to switch from a lambda calculus style application which indirects through the closure record to a C style, push the stack and jump to a known location, fast function call. Right. Then it's going to remove some dead code, perform some more annotation to prepare for finally doing closure conversion, which for the things which couldn't become fast C calls, will allocate closure records on the heap and do all of that sort of fully general functional programming stuff. Right. So that's what Closslang is. So I want to just take you briefly now through the semantics of Closslang, because the semantics of Closslang tells you how these optimizations work and more or less how the proofs work, right? Because what we found, and this is a sort of theorem-proving hint here, is for all of the information that we collect and all of the facts that we want to rely on to do these optimizations, the way to do it was to boost up the Closslang semantics and syntax to include those optimizations and to include those annotations, I should say, and give those annotations some semantic meaning so that in later phases could just rely on the semantics of Closslang instead of some sort of arbitrary facts about some data flow analysis. Right. So the first thing we want to do is if you look at the state that the semantics of Closslang uses in this functional big step interpreter, it includes a bunch of stuff, but importantly, it includes an immutable code store, which is where we're going to put the bodies of all of the C-like functions that we're going to actually be able to jump directly to. And we're going to jump directly to them because the code store is indexed by a number. That's the code pointer. Right. And we also, unfortunately, have to have a maximum application size because there's some sort of runtime stubs that need to be there to support doing multiple argument functions. And so if we don't have a maximum, we have no limit of how many of these stubs we need. Hey, semantics has a state. It also has some values. And because we're talking about closure optimization, the key values that we have here are the closure values. And you can see the closure values are really annotated up quite a bit. Right? So a closure value can just be some closure value that you don't know much about the code for, or it can be a closure value where the previous annotation analysis has told you here's where this closure's body is going to be in that code table. So wherever this closure value ends up, you know it has, the expression there has to have been compiled and put in the immutable code store at this annotated place. Right. The closure is also going to include previous arguments that have been fed into it. Right. Because if I have a multiple argument closure, right, the closures now have arities because they can have multiple arguments. Remember, we're De Bruijn, so we don't need parameter lists, we just need an arity. It may be the case that I have a closure with arity 5, but it's only seen 3 arguments so far. Right, so I'm going to have to keep track of that in the semantics of the language. It's important, this is sort of obvious, but worth emphasizing. arity isn't just the type. Right? Here's a function f that has arity 2. Right? It can take 2 arguments, and then it needs to do something. And then it's going to do this side effect, and then return a function of arity 1. From the type, it looks like it may have arity 3, or it may have arity 1. But in fact, it's a dynamic program. You have to look at the code. It's not type-based, what these arities are. Okay. So lastly, we have the syntax, which also needs annotations. So the function call, so we've got 2 now kinds of function calls. We've got the call expression, which does a C-style function call to the code pointer of the code in that immutable code store in the state of the program. Or we still have a lambda calculus style application that wants to, it has now an optional annotation. So if that annotation is none, this application is just going to indirect through the closure record and do a sort of fully general functional programming thing. If it has some, then the compiler knows that this application is going to apply some lambda calculus style function, but at least it knows where the code pointer is. So it may have to set up the closure on the stack and do a bit more work than the C-style call, but it can still get that direct jump rather than an indirect jump. Right. And then we're also going to annotate each function expression here with the free variables in the function. Right? So that will let us do closure conversion, where instead of copying the entire lexical environment into the closure, we'll just copy the free variables listed here into the closure. Right? And the semantics will tell us that those are the only free variables, because the semantics will look at this and filter the semantic environment to what's here. Right? So that's how the annotations here have operational effect. Right. So we're going to get that known function thing, and we're also going to do this sort of unconditional multiple argument function introduction. So if I've got a function with 1 argument and a function with 1 argument, I'm just going to stick those together to a function with 2 arguments. If I have an iterated application, I'm just going to combine them. And I'm just going to do that regardless. So we do have right to left evaluation, because that makes this a sound thing to do. Right, if you use SML style left to right evaluation, you can't do this unless you know things don't have side effects. Right. So I said, because we have partial applications, we may have a function that has arity 10, but we've only given it 4 arguments so far. So at runtime, we're going to have 2 different kinds of closure records when we finally do the closure conversion to handle this. So there is some sort of complication we're paying to get these fully general, fast multiple argument calls to unknown functions. Right? So one is just, here's a closure you've made, and the other one is, ooh, you fed some arguments in, not quite enough. What should we do now? Right. And so this is where there's a bunch of runtime stubs to handle dealing with these structures. Right. So I haven't said much about compiler correctness, and I'm not going to say much about compiler correctness, but this is the compiler correctness diagram. If you compile your program and run it, you get the same thing as the semantics say you should. Well, these values have to be related in some way. It turns out you can never just compile this value to that value. The existential quantifiers don't work, and your induction never goes through. You always need some sort of relation. And this relation is complicated because it's relating values which have closures, which contain code, which is going to change. Right? So a lot of the work is setting up the sort of relations to allow you to complete this picture and do your proof. And there are 2 kinds of relations you might use. You could use a semantic relation, sort of a logical relation, that looks at how does the closure behave, or you could use a syntactic relation that looks at what does this closure sort of look like. You'll have to look in the paper to see anything about that, because I'm out of time. So during the questions, you can look at this performance chart, which is normalized OCaml on the left, KCaml all the way on the right, how long it takes to do some micro benchmarks. Thank you.